Light travels insanely fast, but how do we actually know its speed? And how do we know how much power it's carrying before it hits you? So this is how physicists measured the speed of light and how to calculate the actual energy that's delivered by electromagnetic waves. First, this is how we measured the speed of light before we had lasers and satellites. What Galileo tried to do was measure the speed of light using hills and lanterns on these hills, but it didn't work because the speed of light is too fast. As soon as this illuminates, even if you're standing here, it's going to illuminate basically instantly. It's hard to measure without advanced technology. Then came along this guy, and his name is spelled like this. And it was in the 1600s, he noticed that the orbit of Jupiter's moon varied slightly depending on where Earth was in its orbit. And he concluded this: light speed is not infinite. It is not instantaneous. Light does not just teleport from place to place. There is a finite speed. However, it just takes time to travel the extra distance. The first accurate measurements came from this guy named Albert Michelson, and he used a pretty cool setup, which I'll show you here. He had a rotating mirror like this with 8 sides, and it would spin. The light would bounce off here to a stationary mirror. You would have an observer here, and you would have the light source here. So it bounces here, bounces to the stationary mirror, back to the spinning one, and then to the observer. If the mirror rotates just right, the light will hit a telescope. If it's too slow or too fast, it's going to miss. And by the way, he used mountains for this. The mirrors were something like 35 kilometers apart. And by syncing distance and timing, he found the speed of light is this number here, 2.99792458 times 10 to the power of 8 meters per second. This value is now built into the definition of a meter. We define a meter from the speed of light. And now we're getting into some math. So light doesn't just travel, it carries energy. It's a wave, of course. And electromagnetic waves, if you remember, are 2 fields. So there's the electric field and there's the magnetic field. They both store energy. The electric field, which we'll represent as the up and down red one, stores energy, and the variable is U of the electric field, equals 1/2 this constant times the electric field squared. That's the amount of energy this electric wave carries. The magnetic field, which is the left and right perpendicular one, stores this much energy, 1/2 electric field squared times this constant. And these 2 formulas are on the free cheat sheet in the description, but how do we find the total energy density carried by this electromagnetic wave? The total energy density in the wave is U equals this constant, E squared. Why? The magnetic field is given by electric field divided by speed of light, E/c. And we can plug it into the full energy equation like this. The full energy equation should be a combination of both the electric wave and the magnetic one, because they contribute equally. So the electric one here plus the magnetic one. But in place of B, we're going to sub in E/c, which gives us 1/2 times E/c squared in place of B divided by 2. Once everything's cancelled out, you get this, which is the total energy density carried by the wave. And you can actually do it the other way around if you prefer the magnetic version, which is B2 over this constant. Either way, it's the same energy, but it's just expressed through different field strengths. Let's go even deeper mathematically. We know that electromagnetic waves carry energy, and this energy is stored in the electric and magnetic fields. But how exactly does this energy move through space, and how do we calculate how much arrives when it hits a surface? First, total energy density, which we just found, and there's 2 variants, a magnetic one and an electric one. This is how tightly packed the energy is in space, but it doesn't tell us the speed at which the energy moves. This is where intensity comes in. So energy flow equals energy density times volume flow. What does this mean? Imagine your wave is sweeping through an open window, and this window has an area A, and it sweeps through this area of A in a short time interval t. Since the wave travels at the speed of light c, the wave front, which are these, moves forward a distance of, say, x, which is equal to the speed and the duration. Because remember, distance equals speed multiplied by time. Distance, speed, time. This means that the volume of wave that passes through, and remember, volume can be found with length times area. So x times area, which is A. And since x is equal to ct, then it can be written as A, E. That's the amount of volume that passes through. And the total energy that passes through is equal to the density multiplied by the volume. So the volume tells us how much, and the density tells us how tightly packed it is inside this how much. So total energy equals wave density, which is here, multiplied by volume, which is equal to this in place of wave density multiplied by volume, which is A, C, T. This is the total energy that crosses this area in the time interval T. And now we're ready to define intensity. Before we do that, I just want to remind you that every single formula and every single equation is on the free cheat sheet in the description. Intensity is energy per second per square meter. It's the amount of energy that hits every unit of area every second, which is total energy divided by area and time. Total energy is this, which is written like this, divided by AT, and you can cancel these, which leaves you with this. Doesn't this look a little bit familiar? And this is the power density of the wave, which is how much power per unit area is hitting a surface. We can also write it with magnetic field, and the variant looks like this. It's basically the density equations, but you throw in the speed of light. That's it. That's for intensity. Or if you want to go even one more step further, you can write it like this. I equals EB over root and their constants. Or like this. It's like the combination of the two. This shows that both E and B participate equally in carrying energy. So the wave's ability to deliver energy comes from the product of the two. This was a lot of math, but let's look at average intensity. So for real electromagnetic waves, the fields oscillate following a sine pattern. And we take the RMS, which are the root mean square values. The root mean square values of electric field is max E over root 2, and same for RMS of magnetic. And this means that average intensity is this. It's the intensity equation, but we added RMS. And this is equal to 1 over 2, this constant, speed of light, E2, 0, which is equal electric, magnetic to this 0. You don't have to understand this, but this is the equation that you actually use. It's what you actually measure when sunlight hits your solar panels or your skin. So the interpretation is this: electromagnetic waves don't just store energy, they deliver the energy. And the higher the strength of the fields, the more intense the wave is, and the faster the wave moves, the more energy it delivers per second. And because the speed is always the same, since all electromagnetic waves travel at the speed of light c, then that means the only thing that affects their ability to deliver power is how strong the fields are. That's entirely what it depends on.